Okay, students, so let's start with the topic of elastic deformation. These are theory past papers of elastic deformation. This is applicable for O levels and IGCSE both. So let's start with this question. Figure 1.1 shows a steel spring. Okay, this is a steel spring. Describe an experimental procedure for obtaining the results needed to plot an extension versus force graph for this spring. You have to plot an extension versus force graph for this spring. What will you do? First step, measure the original length. Measure the original length, or you can say initial length. Measure the original length, or you can say initial length using a meter rule. Using a meter rule, okay. What will be your second step? Attach a known mass, attach a known load, I would say. Attach a known load. For example, 2 Newton from one end of the spring, from one end of the spring, and measure the new length, and measure the new length. Measure the new length of the spring. New length of the spring. The difference between the lengths, the difference between the length, the difference between the lengths gives you the extension. Between the lengths give you extension. Is equal to extension. Is equal to extension. What will be your last step? Repeat the process. Repeat the process with multiple loads. With multiple loads to get some more points. To get some more points. And then last point, plot the graph. Plot the graph of force versus extension. Let's further move ahead. In an experiment to obtain results for an extension load graph, a spring is stretched beyond the limit of proportionality. If the spring is stretched beyond the limit of proportionality, what happens? It becomes easier to stretch and it curves towards the extension axis. It curves towards extension axis. It curves towards extension axis. Towards extension axis. Okay, so let's do that. Initially, you will have a straight line like this. Then you will start to curve towards the extension axis like this. Simple. Let's further move ahead. On your graph, in figure 1.2, mark with a label P, the limit of proportionality. Limit of proportionality is the point till where the force versus extension graph is linear. This is your point P. Okay. Let's further move ahead. The limit of proportionality of the spring occurs at this load. Okay. The extension of the spring is 0.014 when the load is 3.5 Newton. You have to calculate the extension when there is a load of 5.5 Newton. So simple ratio method. Force ratio extension. We can apply ratio method. When a force of 3.5 Newton was being applied, the extension was what? 0.14 meters. When a force of 5.5 Newton will be applied, what will be your extension? Let's calculate that. X is equals to 5.5 into 0.014 divided by 3.5. Can you calculate the extension here? Yes, you can surely do that. Let's do it with a calculator. 1 second. Yeah, the answer comes out to be 5.5 into 0.014 divided by 3.5. This equals to 0.022 meters as your extension. Simple. Let's further move ahead. A student suspends a spring from a support. He attaches different loads to the lower end of the spring. For each load attached, he measures the extension of the spring. Figure 3.1 shows the extension versus load graph obtained. This is your force versus extension graph. Okay. The extension of the spring is directly proportional to the load. Okay. State two features of the graph that show this. Firstly, passing through origin, and secondly, it is a straight line. Firstly, passing through origin. The graph passes through origin. You can say that. The graph passes through origin and passes through origin. And what else shows that force and extension are directly proportional? The graph is a straight line. The graph is a straight line. Simple. Let's further move ahead. Let's see part B. Describe how the student can show that the spring reaches its limit of proportionality at 8 Newton. We have to show, the student has to show how the spring reaches limit of proportionality at 8 newtons. Okay. So first of all, the student will apply or attach a weight, or you can say load, greater than 8 Newton. For example, in this case, let's say 10 Newton. For example, in this case, we can apply 10 Newtons. Okay. Once you apply a load greater than 8 newtons, and if you have exceeded limit of proportionality, what will happen? You will get an extension greater. See, here when limit of proportionality wasn't reached, you have applied a load of 8 newton, you are getting an extension of 6. So that means you are applying a load of 8 newton, you are getting an extension of 6. That means for every 2 newton increase, you are extending by 1.5 centimeter. If you increase the load by 2 newton, your extension increases by 1.5. Same here, same here, same here. But after limit of proportionality, if you increase the load by 2 newtons, let's say you go from 8 to 10, your extension will increase by a value greater than 1.5 centimeters. Let's say it will increase by 2 centimeters maybe. Why? Because after limit of proportionality, the spring becomes easier to stretch. So how will you write this answer? Attach a weight load greater than 8 Newton. You can further write that if the increase in length, or you can say extension, is greater for the same load increase, is greater for the same load increase, then the spring has reached limit of proportionality. Then the spring has reached limit of proportionality. Limit of proportionality. Simple as that, nothing complicated here. So this is how you will write this answer. Let's further move ahead. The spring is used in simple device known as an accelerometer, okay, shown in figure 3.2, okay. The spring is fixed at one end and attached a mass of 5 kg at the other end. Okay. The mass rests on a smooth horizontal surface. There is no friction between the mass and the surface. Okay. The whole device is placed in the car. The car accelerates and the student notices that the extension of the spring is 5 centimeter. Calculate the acceleration of the car. Okay, we have to calculate the acceleration of the car. First and foremost, what can you do? You can come here and see that at an extension of 3 centimeter, we have a force of what? 4 Newton. Okay. So your force is 4 Newton at an extension of 3 centimeter. What is the mass of the car? 5 kg. Can you calculate the acceleration? Yes. F is equals to ma. Your force is 4 Newton. Your mass is 5. Can you calculate the acceleration? Acceleration is 4 over 5. That is 0.8 ms minus 2. Simple as that. Let's move on to the next question. Figure 8.1 shows an elastic rope. Okay. The unstretched length of the rope is this. Okay. This is the length when no load is being applied. Unstretched length are basically the lengths when no load is being applied. Okay. A student uses the hook at one end to suspend the rope from a shelf and hangs an empty paint can of mass this. Okay, this is the mass of empty paint can. Okay. The rope stretches to this length that is 0.97 meter but does not exceed limit of proportionality. Explain what is meant by limit of proportionality. The point up till where? The point up till where? The force versus extension. The force is directly proportional to extension. Simple as that. Proportional to extension. The point up till where the force is directly proportional to extension. Simple as that. Yeah. State what is meant by mass. We have done this several times. State what is meant by weight. Already done that. The gravitational field strength is 10. Calculate the weight of the empty paint can. So the mass of the empty paint can is 0.7 kg. Can you calculate the weight? Yes. Weight is equals to mg. Your mass is 0.7 multiplied by 10. Your weight comes out to be 7 Newton. For the rope, calculate a value for load over extension. Load is 7. What was extension? Your unstretched length is 0.8. Your final length is 0.97. Can you calculate extension? Yes. 0.97 minus 0.8 is your extension. 7 divided by 0.97 minus 0.8. This gives you an answer of 41.1 Newton per meter. Simple as that. Let's further move ahead. The student repeatedly pours some small volumes of paint into the can. Okay, so the student is pouring small volumes of paint into the can where there is 2.5 into 10 raised to the power of minus 3 meter cube of paint in the can. The total length of the rope is this. This is where the rope reaches the limit of proportionality. Okay. Determine the mass of the paint in the can. We have to determine the mass of the paint in the can. We have to determine the mass of the paint in the can. Okay. So, if your rope has a length of 1.7 meters, what will be your extension? 1.7 minus the original length that is 0.8. So, yeah, I guess 0.8 was the original length. So, your extension comes out to be what? 0.9. Don't you think? Yeah. This comes out to be 0.9 meters. Okay. And if you see the previous part, oh, sorry for that. If you see the previous part, you have calculated what? You have calculated the spring constant K. This is your spring constant K. Spring constant K used to be equal to what? Force over extension. That is K. If you have the spring constant, if you have the extension, can you calculate the force? Yes. Force is equals to KE. Okay. What is your spring constant? 41.1. What is your extension? 0.9 multiplied 41.1. This comes out to be 36.99 Newton. Obviously, this can be written as 37 Newton. This is the force. This is the force. So, this force which we have calculated, 36.99 Newton, is the force of the paint can and the can itself. It is the entire force of the can plus the paint. This force, let me write it here, has a problem with it. It includes the force due to paint plus the empty can. Do we have the mass of the empty can? Yes, 7 Newton. Can I subtract it from this? Yeah, I can do that. Force due to paint only is 36.99 minus 7. This comes out to be 29.99. That is roughly equals to 30 Newton. The force due to only paint, the force due to only paint is 30 Newton. Can I calculate the mass of the paint? Yes. If the force is this, you can apply force. This force is equals to your weight. Weight is equals to mg. 30 Newton divided by 9. We have to take gravitational field strength as 10 or 9.8. Let me see. Yeah, we have to take gravitational field strength as 10. Whenever the question is stating you what gravitational field strength you have to take, you will have to obey the question. Otherwise, you will take 9.8. This comes out to be your mass. Mass comes out to be 3 kg. A very, you can say, lengthy question for 3 marks. Let's further move ahead. The student continues to pour paint into the can until there is a volume of this. Okay, it has already exceeded limit of proportionality. He notices that the elastic rope becomes harder to stretch. Oh, that's a strange thing after limit of proportionality. He plots a graph of the total length of the rope against the volume of the paint added. Okay. On figure 8.2, sketch the length versus volume graph from 0 to 5 into 10 raised to the power of minus 3. So from 0 till 2.5, from 0 till 2.5, you will have a straight line. And after that, contrary to your expectations, you will have a decreasing curve. Why? Why not an increasing curve? Because this spring is quite strange and it becomes harder to stretch. If any spring becomes harder to stretch, it will bend towards the volume axis, or you can say the force axis, and not towards the extension axis. So, this is your graph. The student suddenly removes the can from the end of a stretched rope and it contracts. The rope jumps into the air. State the energy change that is taking place in the rope as it contracts and jumps into the air. So basically what is happening? Elastic potential energy. Potential energy is getting converted into what? Gravitational potential energy due to its height and kinetic energy due to its velocity. Let's move on to the other question. In an experiment, a student takes measurements and determines the extension of a spring for different loads. Okay. The apparatus is shown in figure 2.1. Okay. The apparatus is shown in figure 2.1. Okay. Only some of the extensions are shown in the table. Complete the table to show all the extension. We have to complete the table to show all the extensions. So let's examine the table. Okay, so let's see this. The table in figure 2.2 shows the results. Okay, so if you are increasing the load by 1 Newton, your force increases by 35 centimeter. Here, your extension increases by 35 centimeter here. Okay, and you can say this is your unstretched length or L naught. Okay, you have to complete the table. Okay, at a load of 4 Newton, your total length of the spring is what? 350. What will be your total extension? If this is your length, you have to calculate extension. How will you do that? 350 minus the unstretched length, that is 200. 150 comes out to be your answer. Now let's move on to the second length. This is your 420. 420 minus the initial length of 200, you will get the extension again, that is 220. Okay. Calculate the load that produces an extension of 49 millimeter. Okay, we have to calculate a load that produces an extension of 49 millimeter. Can you see if I am increasing the load by 1 Newton, the extension is 35 millimeter. For 1 Newton, the extension is 35 millimeter. For 49 millimeter, what will be the load? For an extension of 49 millimeter, what will be the load? Cross multiply it, x comes out to be 49 over 35. This comes out to be 49 divided by 35. This is equals to 1.4 Newton as your load. Let's further move ahead. The student pulls a load downward from position A to B and holds it fixed at B as shown in figure 2.3. Okay. It is stationary at A and stationary at B. The load has no kinetic energy at either point. Okay, it's pretty evident. At B and at A, there is no kinetic energy in this spring. Okay. Place ticks in the boxes to show how the value of each of the forms of energy compare at A and B. Can you see B is more extended? The spring B is more extended. So obviously the energy stored in the spring at B will be larger. Can you see A is a greater height? So the gravitational potential energy at A will be larger. Okay, let's further move ahead. Work is done by the student to pull the load downward. The law of conservation of energy states that energy cannot be created and cannot be destroyed. Explain how this principle applies in this case. Okay, so we can say work done by the student by the student increases, or you can say gets added up, gets added up to the gravitational potential energy at A to give the total elastic potential energy at B. Simple as that. Let's further move ahead. A spring is taken from a drawer in physics laboratory. Figure 8.1 is the extension load graph for the spring. Okay. Use figure 8.1 to determine the load on the spring when its extension is 4.9 centimeter. So let's zoom in a bit. When the extension is 4.9 centimeters, that means roughly here at this point, your extension is, if I, oh, at this point, your extension is, let's say, 0.82 Newton. At an extension of 4.9 centimeter, your load is 0.82 Newton, as far as I can read. The point X on figure 8.1 shows the limit of proportionality. On figure 8.1, sketch a line to show how the extension load graph might continue after point X. So the extension load graph will bend towards the extension axis, somewhat like this. Let me draw it correctly. The extension load graph will start to bend towards the extension axis. Okay. A rectangular plastic block is suspended from the lower end of the spring. Okay. Figure 8.2 shows the bottom 3.5 centimeter of the plastic block in the water in a beaker. Okay. The density of water is this, the gravitational field strength is this, the base of the plastic block is a square of side 4 centimeter. Calculate the pressure due to water at a depth of this. So pressure is equals to rho g h. What is your rho? 1000. What is your g? 10. You are provided with the g as well. What is your h? 3.5 centimeter. Convert it into meters. 3.5 divided by 100. 3.5 divided by 100 multiplied by 10 multiplied by 1000. Your pressure comes out to be 350 pascals. Simple as that. Calculate the upward force on the base of the block due to the pressure of water. Okay. We know pressure is equals to force over area. If we multiply pressure and area, we will get a force. The pressure is 350. What is the area at the square? 4 centimeter. 4 divided by 100 into 4 divided by 100. This will give you your force. Let's calculate that. 0.04 into 0.04 into 350. This comes out to be 0.56. Your force comes out to be 0.56 Newton. Okay. In figure 8.2, the extension of the spring is 4.9 centimeter. Okay. Here, the extension of the spring is 4.9 centimeter. That means the spring is experiencing a force of what? The spring is roughly experiencing a force of 0.82 Newton. Okay. What else is given? Use your answer from part A and part B2 to determine the weight of the block. Okay. So the weight of the block might be acting like this. Okay. This is your weight of the block. Okay. And what else do you have? Use your answer from part A1 and use your answer from part B2. Okay. To determine the weight of the block. Okay. That's pretty easy. Okay. There is an upward force on the block that we have just calculated 0.56, and there is a downward force that is weight. Both of them collectively give a resultant force downward of 0.82 Newton. So you can say weight minus 0.56, that is the upward force, gives you a value of 0.82 Newton. Now, can you calculate weight? Yes, weight is equals to 0.82 plus 0.56. plus 0.82. This comes out to be 1.38 Newton is your weight. Simple as that. This marks the end of past papers for elastic deformation. If you have any questions, you may ask.